Recordings, okay? Yes.
So, question about the homework. Is it due on, because Gradescope says 5 and then D2L says midnight?
Oh, D2L rules, man.
Okay, so midnight.
Yeah, I'll send Raphael an email
Okay.
telling him that it'll be due at midnight. Does that help out people that haven't started it yet?
Who says they didn't start it?
Yeah. I wasn't talking about you. I'm sure there's somebody. Yeah, so whatever D2L says, I just tried to give you a little bit extra time this week. I would also say that you might want to wait to do the quiz until after you get the homework solution back, after it's due. Might be helpful. I don't know. It's just a recommendation. It's not that you have to do that. It's on the same material. I usually post it the day after the homework's due, so it'll be out there. What else? Oh, recordings. Speaking of recordings, so I've had some people ask me about providing you the recordings. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 27. So I've done it in my other class, and the reason why I'm hesitant is, as you can imagine, if I'm just going to give you guys the recordings every lecture, I think I'll see fewer and fewer of you every class period. Okay, so I've struck a compromise with my other class in that we decided that if 80% of the class shows up, I will post the lectures that are recorded. Okay, we are not there right now. There's 44 of you that are supposed to be in this class. There's only 27 of you sitting here today. So let's try this. Spread the word, okay? See if you can convince some of your classmates to show up, okay? I don't care if you guys all get together and make a schedule, and some of you are gone, but as long as you get the 80%, so that'd be, yes?
So what's the reason behind the 80%?
Because I don't want to see fewer and fewer of you.
Yeah.
I want you guys to earn this, right? This is supposed to be in class. I feel like you get the most value out of being in class. For years and years, and I know things change, okay? And my gripe against the fact that I never got this shit recorded for me when I went to school, okay, is no reason to not give it to you. I feel like you guys deserve the extra, advancement in technology that we have and the fact that I can record it. But I also want to incentivize people to be here, okay? What if I dropped it?
It kind of sucks because, like, with the school saying you have to wear a mask and not available for the hybrid classes,
Yeah, it's in class, right?
And
So
I know you don't
yeah, this isn't. Yeah, not my deal. Okay, all I'm saying is, I want you guys to be here. Okay, the school had to make a decision on how they oriented their classes last spring. Okay, so they were assuming that we wouldn't have to be dealing with this still. And so I think there is an added benefit that we are in this class and not in the sub. Okay, Brennan was in the sub. That sucked, right?
It was horrible.
Horrible. Okay, I was speaking to the same number. Well, actually, only 12 students showed up every class period out of 40. Okay, and I didn't blame them because the screen was this size, and the room was 3 times this size. Okay, I was speaking in the sub ballroom, and so I mean, with that, I can't do much about it. All I can tell you is I want you to be here. Okay, and I'm happy to reward you for having most of you guys here, in that giving you the added benefit of having the ability to go back and watch all the lectures, okay, if that's how you want to do it. Okay, what if we make it 75%? Does that seem fair?
It still seems like a stretch for getting everybody in.
You think so? Fuck, 70%? Can we land on 70? I'm not going any lower than that. Look, you guys didn't even have to do shit, and I went to 70. Yes?
What if you just put the videos on Google Drive, and when people who showed up in class get the link to...
That's such a pain in the ass. That's the problem. It's like, so we'd have to have a sign-up sheet. You guys sign in when you get here, and then I go out, and then I give...
Write it on the board.
So much work.
Yeah, that's too much work.
You signed in with the password, but then I guess that could get out.
Yeah, that's too much. Maybe try and spread the word and convince your peers. It's like, hey, 75%. So let's just say out of 40, right? You would need 30 people. We're at 27. We're pretty damn close. right? You don't think you can convince your peers to show up? You just don't want to be here, the mask or whatever. I don't even like, I don't really care about the mask thing, okay?
Not that hard.
You're paying for it, show up to the bus.
Yeah. Okay, that's where we'll land, all right? Now we get on to the stuff that you guys are paying for, which is learning about columns, okay? Whether or not you want to pay for it. So we started talking about columns on Wednesday, right? These long, slender members that are induced with a compressive load, okay? We talked about Euler, Leonard Euler, I think is his name, okay, who was super bored and decided to come up with solve the differential equation for buckling and figure out what is the critical load at which, based on material properties, right? Modulus of elasticity E, the moment of inertia, so that is the stiffness or your resistance of a cross section to accelerate rotationally. Okay, you guys got some of that in statics, I believe. And then the length of that column between its fixity points, you can figure out what is the load at which it buckles, like you would a ruler, okay, between your hands. And then if we just substitute in the fact that stress is force over an area, we can figure out this critical stress that is induced in this member when it buckles. And based on that, the equation simplifies to pi squared E over L over R squared, R being the radius of gyration, which we'll talk about. And this solution is for a pinned column like we see here, okay, with n modes of buckling, as I mentioned. N modes, as you can see here, we have our first mode of buckling, which would be one buckled shape. Then you have the second mode, which is a potential, right? And as you can see from the solution has n squared in the numerator. As our number of modes goes up, that critical buckling load goes up as well. All right. So some things to think about. Running out of room here. If we graphed L or L over R and P critical or our critical stress, right? So L or L over R is essentially the brace length, right? How long is our column? And then we figured out, we plotted different points for a given cross section, right? With a given modulus of elasticity and a given moment of inertia. We would get a curve that looks something like this. Okay. Essentially, we exponentially increase our ability to carry axial load as we decrease the length, right? You can think of that like this big ass piece of rebar, right? Me squishing on it right here in front of you, it's going to be able to carry a shitload of load. But as we continue to make this rebar longer and we still put axial load in it, as we get longer and longer, that load drops off quicker, like really, really fast right at first, and then it starts tapering off, okay? So if we looked at some of this behavior, we could say our P critical or our critical stress is inversely related to length. Okay? So the longer the column is, the lower our ability to carry load. I think that makes sense. As our modulus of elasticity goes up, so does our critical stress and our critical axial load, right? So our modulus goes up, our ability to carry load goes up, right? We're essentially increasing the stiffness. If our moment of inertia goes up, then our ability to carry load goes up, right? If we increase our cross section's ability or stiffness to rotate, then our forces go up. nowhere in this equation do we see the yield stress, right? Or the strength of our material. So it's not a function of the strength of our material, but it is a function of our stiffness, okay, our modulus of elasticity. And as you can see, this graph, as we get lower and lower, we'll eventually get to a point where it actually won't buckle, but we will truncate it at our material strength, right? So at some point, we're gonna have more strength because it's not gonna buckle, but in reality, we're gonna yield. We're gonna hit some sort of material plateau in our column. Well, not all columns are pin-pin, okay? That's a pretty ideal column, right? Sometimes we can have a fixed pin column, right? Maybe you decide to embed a wide flange, right? This would be a wide flange section, an I-beam, okay? Maybe you embed this into the ground. The lateral system, what carries at Langford, I think it's Langford, there's like a little dining common area as you first walk into that dorm area, okay? That whole building is carried laterally by big wide flange sections that are buried in concrete piers in the ground. They're just cantilevered out of there, okay? So the loads that are induced on those columns would follow this kind of fixed pin methodology, right? It's fixed at the base, it's not allowed to rotate, okay, or translate. And then at the top where we have all of our roof framing in, it'd be more like a pin, okay? And then in some cases we might have a fixed column. It might have enough rotational restraint at the top where it doesn't want to let the column rotate. And then finally we have a fixed free column. So that would be one where it's not allowed to translate, or it's allowed to translate and rotate at the top. Essentially a cantilever, okay? Well, to figure out, when you can't see with shit, can you? So we got a new solution for this, right? This P critical that we had before, this is for our idealized column. Well, Euler went back through and calculated what the capacity is based on these different fixities, and he developed this equation. So now our critical force, or our critical load, P, okay, is pi squared EI over this term KL squared. Well, this KL squared is what we call L sub E, or our effective length. And if we go back through and we divide by area, we end up getting this equation, pi squared E over that effective length, KL over R squared. And this is called KL over R is effective slenderness ratio kind of, sort of. Okay. So built into this equation, we essentially need to figure out what is our effective length. So our column's going to have length. Yes, Brett?
In the first equation, is the L in the denominator supposed to have subscript E?
No, this entire KL equals,
Oh.
so KL equals this effective length, L sub E, okay? And we get L sub E with this factor K. And if you look at this image here, it kind of gives you, well, it does, it gives you different K factors for different fixities of our column, okay? Yes. So when you get to our pin-pin model, which this is calibrated for, this is what Euler solved this for, okay? our K factor is 1, so the length is 1. I won't get into as much of the details, but it's based all off of a sine wave, so you can imagine this. This is one big sine wave that's running through our column. This is 0.7 a sine wave, this is half a sine wave, this is 2 times a sine wave for a cantilever. Essentially, as you look through here, it's modeled as a pin-pin. Well, if you add some fixity, you reduce that factor, right? Now it's 0.7. You add some rigidity, add some stiffness, you're restraining the column from buckling out. If you do that, your effective length goes down. Well, if your length goes down, then your strength goes up, right? Same with fixed case. Well, we're gonna make your length even less. We're gonna say it's half the length is your effective length, because you have stiffness that's keeping our column from buckling out, and so our capacity is going to go up even more. A fixed free condition, or this cantilevered condition, right, the K is 2, so you essentially double the length of the column because you have less fixity, right? So I think all of those make sense. One of these terms in here is the radius of gyration, or R. That is simply the square root of I over A. Slenderness ratio, well, that's our effective length over R, which is KL over R. One of the big items in this equation is our moment of inertia, right? I. Well, you guys remember calculating some of this, right? So I is our moment of inertia, and we have a 3D world, right? We live in a 3D world. So we need to look at right, you did some of this in statics, right? Moment of inertias. Remember this? Okay. So it's essentially, if we looked at this cross section, right, this rectangular cross section, and we put a coordinate system, right? Same with this I shape. If we put a coordinate system of y and x, right? Our moment of inertia about the y is the resistance for this section to twist about that axis, right? And then with the x direction, it's the resistance to twist in this direction. And so we effectively, for this column, for instance, we have the ability to buckle in both directions, right? It could buckle in and out of the page, and it could buckle in the plane of the page, right? And there's the possibility that we might have different fixities in those in those two directions, right? Could have different effective lengths. Maybe it's braced this way at mid-height, but then not in this direction, right? So we need to go through that, and we'll analyze both those cases. And to do that, we need the moment of inertia in both directions. All right, so we've got IX, we've got IY. For a rectangle, if you remember, BH cubed over 12. IY is HB cubed over 12. And if H is greater than B, then IX is greater than IY. So you need to be pretty comfortable about calculating this, right? Rectangle is pretty simple. Well, An I shape is essentially a series of rectangles. If you remember in statics, assume you did the parallel axis theorem, right? Essentially coming up with the moment of inertia about the centroid of a section, okay? It's essentially the moment of inertia of all of these three rectangles, some of which transformed into our centroidal axis, right? Well, as engineers, we don't like to do things that we don't have to, okay? Sometimes you're gonna have to calculate the moment of inertia, but a lot of times, all this shit is out there for you, right? Somebody who's already done it for us, we don't have to do it twice. So we do have these tables, okay? This is in Appendix B in the text. So you gotta actually go out there, go to the Wiley resources, go to the e-text, go to the chapters, and at the very bottom it'll say appendices, and you can find these tables, okay? And you'll need them for the homework for next week. But in these tables, okay, for instance, this is a standard channel, okay? So a C shape in steel, okay? Some of you probably are unfamiliar with this, but in steel they have designators, okay? This is what they would call a wide flange, so it would start with a W, okay? But the designation is the same. So a C12 is a nominal depth of 12 inches, okay? Times 30, well that's the weight of this section per foot, okay? So this might be, see this is probably an 8. So this is like a W8 by 13. 13 pounds a foot. Nominal depth is 8 inches. It's really probably 8.15 or whatever, but they classify it as nominal depths. And then you'll see them in these tabled values. So if you see it in a homework problem, it says W12 by 35, right? You know that this column that they're talking about is 12 inches deep and it weighs 35 pounds per foot. They can get ridiculously large. I've seen W14 by like 4 something, okay, for like big high-rise columns, okay. Flanges are like multiple inches thick. So pretty impressive stuff, and they roll these out in the steel mills. So we have these channels. The other thing, if we don't have a designated shape, okay, this is where I went, and I actually took Appendix A out of the text, and I put it into our lecture notes section, okay, for the class. So geometric properties of an area gives you a little review of what the moment of inertia is, but then it gives you a lot of these stock equations, right, expressions for the moment of inertia about each of these sections. Any questions there? So as I mentioned, this is nominal depth. This is weight per foot. We also have I shapes, which are called wide flanges. We have HSS sections, right? So this would be, say, a W12 by 22 is a good shape. HSS section, those stand for hollow structural sections. And there are round ones. There's rectangular ones, there's square ones, and there's round ones, and they're not pipe. They're different, okay? Pipe comes in schedule sizes. HSS comes in diameter and weight. There's also angles, right? 4 by 4 by quarter, something like that. Obviously leg lengths, and then the thickness of each leg. All right, we're going to do a column example. All right. So we have 2 channels. They're both C12 by 25, so 12 inches tall, 25 pounds per foot. And they're used for a column that is 35 feet long. 35 feet long. I mean, that's like super tall, okay? assume pin connection at each end of the column. We can use the modulus of elasticity for steel, which is 29,000 KSI. It's always that. And they ask us to determine the total compressive load required to buckle the two members if they act independently of each other, or if that lattice, that blue lattice work that's shown there, okay, if that's in place and sufficient to make this one section. Okay, lattice back to back is shown. Well, as we know from up above, we have our P critical equations, right? Our P critical equations need the moment of inertia, right? Area, that goes into the radius of gyration, right? So I'm going to go out to Appendix B for a C12 by 25. And I'm going to grab the area, right? C12 by 25. So if we go up here, that's this row right there. So I've got it here. So I'm going to write down the area. The area is 7.34 inches squared. Moment of inertia about my y-axis. Well, we got to be careful when we look at our y-axis, make sure the orientation is right. Well, in each of these tables, they give a little diagram depicting what axes that they assumed for the local coordinates of this channel, right? So we've got x running horizontally, which is typical. So I'm going to just write that up here so that I remember. We have x and we have y. Right? So I sub y, that from our table, is 4.45 inches to the fourth. We know the length of our column is 35 feet. We know we're going to need to come up with some effective length, right? Effective length is K times L. They told us it was pin-pinned. So if we go back up here to our different fixity types, right, at the end, if we go to pin-pin, well, that's our standard case. So our K value is 1.0. I also really want to know what IX is. It's 144 inches to the fourth. A lot stiffer, right? You can already see here which way it's more easily going to buckle about. We have our modulus of elasticity. Well, that's 29,000 KSI. And I'm going to grab one more parameter because it's going to help me as we continue down. And that's this X bar. Well, if we think ahead here, if they act independently of one another, right? The centroid of our cross-section is the centroid of each of our individual channels, right? So our moment of inertias that are provided in the table are correct. Well, if we combine these two together, right? In the y-axis, right, the rotation about the y-axis, now you have these two channels that are acting together. So now we have a composite member made up of multiple elements, and the fact that it's composite is going to change its moment of inertia. And so we're going to have to use the parallel axis theorem. And in order to do that, I need to know exactly where the centroid is of this channel. So I want to know what my X bar is. So in this table here, they give us this X bar, right? The distance from the back of the channel to our centroid is X bar. So I'm going to write down X bar is 0.674 inches. Our base equation right, is this KL squared. So knowing this, now we can start tackling our two problems, right? One was if the channels act independently of each other, right? So in this case, we would look at each channel by themselves, and because the channels are both the exact same, we're going to just double our answer. So our P critical total equals our P critical of our channel times 2, right?
If the channels were different, would you add them together?
Yes. Yes. You're making a lot of assumptions, but I think for this class, the simplicity of it, we would just add them together. You'd have to assume that they would share loads equally. So we have our critical force for our channel. We've got two channels, so we add those together to get total. Well, we have two axes. Whoops, that is not how you spell axes. Right, X and Y. So let's start with the x-axis. Well, we have pi squared E moment of inertia, this time in the x direction, KL in the x direction squared. So we got pi squared, 29,000 KSI, 144 inches to the fourth. K is 1.0 times 35 feet times 12 inches per foot. Got to make sure we have consistent units here. We need inches squared in the denominator to cancel out our inches squared in the numerator. That's left over after multiplying KSI in inches to the fourth. So this results in kips. So our P critical in the x direction equals 233.6 kips. And when I denote KL, right, our effective length in the x direction, the reason why I denote it with x is that there's a possibility that your column might be supported differently in the two directions, right? So for rotation about our x-axis, if I had a support on the y-axis that was maybe, say, half the height up, so 17 and a half feet, okay, that would reduce this length, right? Same with in the other direction. But it said it's pinned in both directions. So we're going to now look at P critical in the y direction. Now we got moment of inertia in the y direction, effective length in the y direction. We now get pi squared, 29,000. Our moment of inertia in the y is very, very small. We get a measly 7,000 pounds, just over 7,000 pounds. Huge difference, right? But as you can imagine, if you're looking at this actual C12 by 25, right, the flange width is only 3 inches wide, where the depth of the member is 12, right? It's like a 2x6 or a 2x8, right? It's going to want to buckle, or you don't want to lay that flatwise, right? It's not as strong as it is standing straight up. Same goes for columns. So in this case, the weak axis controls with them acting independently So our total axial critical load is 2 times 7.22 or 14.4 kips. So that's the answer to A. We had these two 12-inch channels. They were 35 feet tall. They were pinned at the top. You could put 14,000 pounds on them. I mean, that's kind of nuts, right? That's a lot of weight. I mean, that's like 2 3/4 ton pickups sitting on this pogo stick that's 35 feet tall. Right? Doesn't that seem ridiculous? That's pretty cool. Steel's nuts. Right? 35 feet tall. You like look out the window and you'd see it just below us. Anyway, you guys don't care. That's fine. I care. That's all that matters. At least that's what I tell myself. Well, now we're going to take it a step further, and they said, well, we're going to connect the flanges of these channels. Okay? So not only are we going to be sitting these two channels down on the ground, right, pinning them at the top and bottom, but now we're going to connect them so that when these try to rotate about our, what was our weak axis, right, the y-axis, okay, they're going to bend as a group. Well, when they bend as a group, they no longer have a moment of inertia of themselves. They have a moment of inertia of the entire group, right? The assembly. So I'm going to go back through and say, go back and to make it easier, 7.34 inches squared. IY equals 4.45 inches to the fourth. IX equals 144 inches to the fourth. This is that X bar that we talked about, which is going to be helpful here. E is 29,000. And L is 35 feet. K equals 1. So for part B, as I mentioned, now we have a composite section. So we need to find the moment of inertia of that composite section. Right? And more specifically, we just need to find the moment of inertia in the y direction, right? Because connecting these two, they never gave us anything about what this lattice work is. So when we look at rotation about the x-axis, right? Whether or not these two channels are connected with that lattice work, they could care less. They're just going to have the same moment of inertia about the x direction, right? Or they'll essentially have twice the moment of inertia, which is essentially what we did already. We doubled it. So we need to find IY of the composite section. Well, here comes your parallel axis theorem, which you guys were probably already jotted down, highlighted it, excited to use it. Right? We have this moment of inertia about any given point, right? Is the moment of inertia about a centroidal axis, right? Or about some point moved to your next point of interest, right? Where you're headed, which is the area of that section times the distance to that point squared, right? So in this case, we've got X bar, right? This is the centroidal axis of each of these channels is between the flanges, right? Remember, getting the centroid is the weighted average of the areas, right? You can figure out what this point is, but they gave it to us. So it's right here. Well, we really want to know what is the resistance to rotation or moment of inertia about this y-axis. So we need to know what this distance is. Well, they gave us the 6 inches, which is the back-to-back distance, but we need to take it from the centroidal axis to that axis. So we need to take half of 6 inches plus that X bar. Right? So the distance between our coordinates of interest, where it was and where we want it about. So in this case, D equals 6 inches divided by 2 plus x bar, or 3.674 inches. So if we look at this equation, now we have the moment of inertia I sub y equals 2 times, okay, if we use our parallel axis theorem, we're going to do this twice, right? We're going to take the channel on the left and move it to the center on the right. We're going to take the channel on the right and move it to the left to the center, right? So I'm just going to do this twice. So I say 2 times. Well, now I sub y, well, that is 4.45 inches to the fourth. Area, 7.34 inches squared. And that d we just calculated, right? That's the distance that our axis is traveling, right? So this is I bar y plus a times d squared. Right? That's what we're doing here. And we're doing it twice because there's 2 channels and we're moving it to the center. And this only works, right, doing it twice because the channels are the exact same channels. If they were different channels, this would be different. So now we get a new I sub y of the whole section of 207 inches to the fourth. Well, if we step back and look at Ix versus Iy, Ix equals 2 times 144 inches to the fourth, right? That was our Ix bar, 144. And looking at the coordinates, right? Our new x coordinate with them connected together, our x-axis, aligns with the x-axis of each of those channels. So we don't get any growth of the composite section of our moment of inertia. Whereas in the y-axis, right, we essentially had these independent channels that were rotating about their y-axis that was between the flanges. And now we're going to move it to the center. And when we did that, we got 207. So we get 288, though, in the x direction. Well, that is greater than 207 inches to the fourth. Well, therefore, Iy still controls capacity. Right? Moment of inertia in the y is less, okay? Because in our P critical equation, everything, right, P critical, pi squared EI over KL squared. Because this effective length is the same in each of our directions, right? Buckling about the x-axis, buckling about the y-axis. Because they're the same, right, and it's the same material, really whichever moment of inertia is larger is going to give us our larger load, right? So the smaller the moment of inertia, in this case, the smaller the load. So if we could just, that's why I made this just straight comparison between our moments of inertia in our 2 directions. And because I sub y is still less than I sub x, then that means I sub y is going to control, right? Things would get a little bit different though, right? If the effective length was different in those 2 directions. If we say had a brace point on the weak direction that was at 17.5 feet up, maybe it was mid-height, you could cut that on brace length in half. You couldn't make this comparison as easily. But if we go through and we calculate this based on 29,207. Again, we have 1.0 as our K factor. We have 35 feet. We're going to multiply by 12 to get inches. We get 335.9 kips. Isn't that insane? That's insane. Say this thing was 12-inch. I wish I had a damn channel. Okay? You have two 12-inch channels. Okay? They're 35 feet tall. And you connect them 6 inches apart, they can carry 300,000 pounds. And they're 35 feet tall. Does that seem nuts? It's nuts. It's like 4 fully loaded tractor trailers. That's like 80,000 pounds a piece running down the road, right? You could stack 4 of them on this spindly ass column of steel, and it would be okay. 335.9 kips. There's a lot of other specifics in there that aren't the case, right? We're smoothing things over a little bit in this class, but for the most part, I mean, holy shit. Okay. Look at that, perfect time. We're gonna start torsion, which I had a hard time finding some cool videos, so maybe I'll take the weekend and try and find some more cool videos. Saw this one guy broke a carbon fiber drive shaft on his like Ford Mustang and had a slow motion video of it. Just like shattered. Yeah.
Not forgetting.
No. Yeah. He looked like he was bored. It was like a lot of cornfields. He looked like he was in the Midwest. And he was out on some random. It didn't say. I mean, I think it said the horsepower. I think it had 800 horse in this Mustang. What's that? Oh no, I don't know. I guess I didn't look at the what the video was, but I was just trying to see like exploded drive shaft, or I also watched a lot of truck pulls where the two guys were sitting on the tarmac trying to pull each other, and a lot of U-joints would fail. Yeah.
Now just watch Jordan Fire, just watch Jane Nielsen beat the shit out of him.
What's that?
I've never watched Jordan Fire. Okay, so as a mechanical engineer, you'll love the house. So they basically bring in these dust plates and stacks in a build.